Hello everyone, let's talk about polyprotic acids. So most of the acids we've been talking about and looking at up to this point have been what are called monoprotic. So monoprotic acids have one hydrogen to lose. And an example of that would be acetic acid, which is what's in vinegar, but it's this hydrogen on the oxygen that's available to be lost. You can also have a diprotic acid where you have two hydrogens that can both be lost. So for example, in H2SO4, both of those two hydrogens out front can be lost. You can have a triprotic acid where you have three hydrogens being lost, as in phosphoric acid. You can also have a polyprotic acid, which is the di and triprotic, but can be many, many more hydrogens. For example, if you have something like DNA or another large biological molecule, often there are dozens and dozens or even hundreds of hydrogens that can be lost on that entire molecule. So when you start losing these hydrogens, that loss or that ionization occurs stepwise. So for example, if I take the carbonic acid molecule, H2CO3, the first hydrogen is lost, and that results in the formation of a hydronium ion and the bicarbonate ion HCO3-. So only one hydrogen is lost initially. This first process is an equilibrium process. Carbonic acid is a weak acid, and the equilibrium constant for this first deprotonation, so I'll call it Ka1, is 4.5 times 10 to the negative 7th. So only a tiny fraction of those carbonic acid molecules are going to lose a hydrogen. Well, you make a small amount of the bicarbonate ion, which can then go on to lose that second proton. And that second deprotonation process, we'll call it Ka2, is also in equilibrium. And this would have an equilibrium constant value of 4.7 times 10 to the negative 11th. Notice that as you have additional losses of protons, your equilibrium constant gets smaller. So you get less and less of the deprotonation process occurring. And that's standard for all weak acids. If you look at what the overall process is then, you have your carbonic acid molecule losing two protons, each to their own water molecule. Well, if you look at the Ka value for this overall process, it's the product of the two individual steps. And so you can see that for the whole process, the equilibrium constant is very, very small. So this is going to have an impact on what we will find in solution. So if we were to dive into a beaker of water that had some carbonic acid dissolved in it, we would find mostly carbonic acid, a little bit of the bicarbonate ion and hydronium, and even less of the carbonate ion. And this has some real implications for trying to calculate the pH of a polyprotic system. First off, since the first dissociation, that first ionization, has a much larger equilibrium constant than the second one, that's what's going to define your pH. That's going to define the amount of hydronium ion in solution. The second, or if it's a triprotic system, third deprotonation happens so much less that it really doesn't contribute a lot of hydronium to the overall system. And secondly, you're going to have only trace amounts of the products from subsequent deprotonation steps. So if you want to calculate the pH of a polyprotic acid, it's not hard. You're going to write a dissociation equation and equilibrium expression for all the dissociation. You're going to make an ice table for that first dissociation because that's really going to determine what your pH is. And then if you wanted to know what the concentration of all those other further conjugate bases were resulting from the second or from the third deprotonation, you could work subsequent ice tables, which is the most rigorous way to do it, or you can assume that the concentration of all those other conjugate bases are equal to their Ka values. And I'm going to show you using an ice table why that works. So let's take oxalic acid, which is a diprotic acid. Let's see what its pH is going to be in a 0.1 molar solution and what the concentration of the oxalic acid and the conjugate base from both the first dissociation and second dissociation will be. Once I have my equilibrium equation and my equilibrium constant expression set up, I'll plug in the values that I know using X to represent the dissociation. So for this first dissociation, Ka is actually really big, 6.5 times 10 to the negative second. So sadly, I can't use our friendly approximation of x being much less than the starting concentration. So you'd actually have to solve this one with a quadratic formula. And you'll find your value for x to be 0.054 from that quadratic formula. And so we can find the concentration of all our different chemical species, and we can find the pH is 1.27. So this first deprotonation is going to determine your value for hydronium. Let's see what the second deprotonation does. So as I go to complete the ice table for the second dissociation, it's important to recognize what my starting concentrations are. So I know from the first ice table that my concentration of that first conjugate base is 0.054. And I know I already have some hydronium in solution, so that concentration is 0.054, but I haven't started out with any of my oxalate just yet. Now some of this is going to dissociate again, and since I already have an x, I'm going to use minus y here because it's a different amount. And then I'm going to take this and use this in the Ka expression for this deprotonation step. So when I go to plug my values in, I see that I have two different expressions, one where y is being added, one where y is being subtracted. But if you look at this value for Ka, 6.1 times 10 to the negative fifth, only a tiny amount is going to be dissociating. And so really, y is going to be negligible when added or subtracted from that 0.054. And since this means we've got 0.054 times y over 0.054, it turns out that y, that value for the concentration of the oxalate ion, is just the same as the second dissociation constant. And then all of our other concentrations are unchanged. So when you're working with a polyprotic acid and you're trying to figure out what the pH is, you only need to worry about that first dissociation. That first dissociation will also allow you to calculate the concentration of the remaining acid form and the conjugate base of that first dissociation. To find the concentration of any further conjugate bases due to subsequent dissociations, because of how little dissociates, those concentrations are going to be equal to your Ka2 values or subsequent Ka values.